Hi everyone, and welcome to the Preparing for the NMR Problem Set video. We are going to go over a couple of basic type of problems to show you how you're going to go about predicting the number of signals in each compound, the integration for those signals, the splitting for each signal, and the chemical shift, both the range and the calculated chemical shift. We're going to start with this 1,2-dibromoethane example. I like to start by drawing in all of the hydrogens. There's a hydrogen here. I'm going to call this hydrogen A. And hydrogen A is the only one like it. There's only one hydrogen there, and that is unique from the three hydrogens that are over here. I'm going to call those protons B, and those are all equivalent hydrogens or equivalent signals because they are all connected to the same carbon, so they have the same chemical environment. Now, the way I have this table set up for you, and there are tables like this in the worksheet that are already given, but notice that there's only one big block, like all of this is just one big block. You need to split it into the number of rows that are indicative of how many types of protons or how many signals there's going to be. So since we have two, I'm going to draw just a line halfway through, and then I'm going to have columns for each one of these. Okay, so we're going to start with signal A. Signal A would integrate to one proton because there's only one hydrogen in that molecule that is next to those two bromines. Signal A is next door to B. There are three B's. Remember, splitting goes by the n+1 rule. So in the case of A's signal, A has three neighboring protons. So it's going to be split into four signals or four peaks, and this is known as a quartet. So again, A has three neighbors, 3 + 1 is 4, and that splitting pattern is a quartet. Now, if you're curious as to how I got that, I'll just scroll back up and remind you that you have this table here that exemplifies the n+1 rule and all the different types of splitting patterns that we've seen, or some of the splitting patterns that we've seen. So here, just to highlight, this is where we said we have three neighbors, so it's splitting as 4, but we actually call that a quartet, and so we would expect it to look something like that. That's a little bit blobby, but 4 peaks with it, where the 2 center ones are a bit higher than the 2 outer ones. Okay, now we'll go back. Now here's where we go to the chemical shift range. We're going to note the chemical environment of H, and that it's, or sorry, HA, and then it's nearby some halides. So now we're going to go over to the NMR tables. And this is table 22.2. This is the general chemical shift ranges. So we're looking for the halides. We have a hydrogen, oops. We have a hydrogen that's next to a carbon that's next to a halide, and notice there's not one where it's next to 2 halides, so we just kind of get as close as we can. So our general chemical shift range, our broad range, is going to be between 2.1 and 4.5. But we can get more specific than that. That's a pretty broad range, and the fact that we have 2 bromines means it could be outside of that range. So this is where we go to, not this next table, because that's for aromatic protons. We don't have any aromatic protons. What we have instead are an alkyl proton. We're going to be starting with the methyne of 1.5 because it was just a CH group. And we'll be looking for the bromine as the group. So as if to say we have a CH, and that CH is connected to some other groups. And what are those groups? Well, we already said that those 2 groups are the bromines. So if they are if the bromines are right next door, which they are, we're going to be using this column here as these alpha substituents. So we're going to be looking down that first column until we find specifically a bromine, and there it is. The bromine is in the alpha position, or just 1 carbon away, so we're going to be adding 1.5 and 2.1, but since there's 2 bromines, you're going to add that twice. So this finally comes back. we start with 1.5 because it's a methyne, a CH, and you're going to add 2 times 1.2, or sorry, 2.1. So I realize I want to keep this area a little bit cleaner. So let me drag this on over. So fun. Boop-a-doop. And we can get a little better of an explanation or like better notes on why this is. So the 1.5 came from the fact that it was a methyne or CH. And then this 2.1 came from this being a bromine alpha substituent, and there were 2 of them. So this adds up to 5.7. Next we go to signal B, 3 hydrogens. Those 3 hydrogens are coupled back to signal A, and there's only 1 A. So the N+1 rule says that we should have 1 + 1 or 2 peaks, and that is a doublet. Okay, a doublet looks like this. Right. Its general chemical shift range is going to be just the regular alkane region because it's too far away from those halides for it to make a big effect. So we go back to the first NMR table. We find just regular old alkanes come between 0.8 and 1.9. So there's not a range here for where it's a hydrogen next to a carbon that's attached to a bromine. This is just the alkane range. So that's the general range again. 0.8 to 1.9. Now we're going to take into account that we have a methyl group. It is a methyl group. Signal B is a methyl group, so that's going to have its own base value. And we're going to add in the fact that we have 2 bromine substituents. So we're going to figure out what that value is in that table. And those are going to be bromine in the beta position, meaning it's 1 more carbon away. So let's figure out what those numbers are. I'm going to go back to, there we go, this table here. And again, we have a CH3 group, and that CH3 group is 2 carbons away from those 2 bromines. So we're going to be, once again, looking for those values. But now we're going to be looking for the beta substituents. We go down until we find the bromine, and we can see that this value is 0.7. So we're going to be adding 0.7 twice because there's 2 of those bromines. To that, we added our base value of 0.9. which I may or may not have highlighted up here. So we're going to be taking our base value here of 0.9. Okay, so 0.9 times plus 0.7 times 2. Okay, so those 2 bromines obviously don't have as big an effect because they're way farther away. This adds up to 2.3, and that's how you figure out a calculated chemical shift. In our second example, we have a new type of functional group introduced. We now have an aromatic ring involved. We have 3 hydrogens here that are identical to the 3 hydrogens there. They're all what we call benzylic protons. I'm just going to add that word in. Those are benzylic protons, and we're going to call those signal A. We then have, A twice, why not? We then are going to have aromatic protons as well. That proton that I just drew is identical to this proton here. They're both ortho to one methyl group and meta to another methyl group. So there's a plane of symmetry. Actually, there's like 2 planes of symmetry here. We have a plane of symmetry that goes through the molecule like this, and a plane of symmetry that goes through the molecule like that. Okay, so all 4 of those aromatic protons are actually identical. That's not always going to be the case, but that's what happens when you have a para-disubstituted ring and those 2 substituents are the same. So those 2 methyl groups are the same, so there's lots of symmetry in that molecule. So we're going to call all of those hydrogens in blue, we're going to call them B. Once again, we just have 2 signals. So we're going to make these together. And by the way, if you're not doing this with the handout, please pause the video. And you can do that at any time. If I'm about to get ready to do a problem, you can always pause the video, try and work it out yourself, and then watch me work through it. But you should definitely have this lecture handout. This is the lecture 6 handout that is on the course website, and I send it to you in an email. Okay, so now let's go back. Once we have now that we know the number of signals, we have signal A that's going to integrate to a total of 6 hydrogens. It actually does not have any 3-bond neighbors. So what we're really looking at, right, if we're comparing like these hydrogens here, we're looking to see if we have any protons on that carbon, and we do not. So there's no neighbors, there's 0 neighbors, N equals 0. So this is just going to show up as a singlet. Okay, so just one single peak. Boom, singlet. We then want to figure out what our chemical shift range is going to be. Remember that A is going to be in the aromatic region, but they are benzylic type of protons. So let's find that. We have 2 aromatic regions. We're going to go for the lower one. It's going to be 2.2 to 3, so you can see this little superscript there that we're dealing with benzylic protons. That means it's the hydrogen connected to a carbon that's connected to the aromatic ring. And that's going to be as opposed to the next one, so we can just, since we're here, where we have the aromatic hydrogens, the ones that are directly attached to the benzene ring, you can see are much more de-shielded. They're much closer to the aromatic ring. All those electrons are kind of floating around doing their resonance thing, so they can't be bothered to provide an electron shield for those hydrogens. So I'll just make that little note. These are more de-shielded than the benzylic protons. Make our way back here. We have our range is 2.2 to 3. And while we're remembering it for signal B, I'll just kind of sneak that guy in here so we don't have to go back to that same page again. We're going to calculate the expected chemical shift for signal A. We're going to have a CH3 group, or a methyl. That's going to be our base value. I'll look up our base value, and then we're going to add in the fact that we have an aromatic group. Now, you may be thinking, oh, we have 2 different methyl groups, so we add the aromatic group twice, but we really just look at it one at a time. So we're just going to focus on like that one, and it's connected to an aromatic ring. Here we are at the additive parameters for alkyl protons. So that is still considered an alkyl proton as opposed to using the other table, which we'll use here in a second. We have, once again, a methyl base value of 0.9 is where we're going to start. Our substituent, which is an aromatic group, is alpha, meaning this guy is going to be an aryl group because it's a hydrogen connected to a carbon connected to an aryl group. So we make our way here. We're going to be adding 1.4 just once. We start with our base value of 0.9. We add 1.4, and that gives us 2.5. Next, signal B is going to be a total of 4 hydrogens. At this point, I'd like to point out that we may, when we're actually looking at the spectra and doing it in the opposite way, it doesn't always come up as 6 hydrogens or 4 hydrogens. Remember, integration is expressed as a ratio, so you may see something like 3 to 2, or the integration could even be like a 1.5 to 1. Oftentimes, the integration is actually given like this because one signal has to be like the standard or the base point. So one signal is integrated as 1, and then everything else is integrated relative to it. So you do need to be given some more information about the compound to know whether the actual number that's given, the ratio that's given, corresponds to 3 hydrogens or 6 hydrogens in this example. All right, but this is moving backwards, like we already know the structure of the molecule. So now we consider that any one hydrogen doesn't have any neighbors. And this is another thing that I haven't really talked about. I'm going to write this out explicitly, that equivalent signals do not split each other. And if you think back to the demo that we did in class, we had some nuclei or some students that were moving randomly, clockwise or counterclockwise. When the actual resonance frequency hit, like at that chemical shift, the central chemical shift, all of the B protons were now going in the same direction. Like they're all going counterclockwise, but any neighboring protons were going in other directions. So the fact that all the B's are at the same resonance frequency means they don't affect each other. They're all resonating. They're all flipped in the same direction. So there's no splitting here. Once again, we have a singlet for both of these. This is going to be two singlets at very different chemical shifts for this compound, para-xylene. So now we are going to figure out the calculated chemical shift, just some things to keep in mind before we switch over to the other one. These are going to be aromatic signals, so there's going to be a specific base value, and all aromatic protons are all CH, so we're actually not going to be caring about like the methyl, methylene, methyne. It's just one simple base value. And we actually have two different things to consider for any one proton, and remember I'm highlighting it's already highlighted. So I'm highlighting this proton here. I'll do that. So any one of those protons has a methyl group, relative position is ortho. It also has a methyl group, relative position being meta. Okay, so you do have to account for both of them, even though they're the same substituent. So let's switch screens. Now we're at 22.4, which is the table where we start with aromatic protons. This is always our base value. This is, if there were no substituents on there, if it were just benzene, it would start at 7.36. And we're going to be looking for methyl groups. And look at that, we already have one. So here's our methyl group. We're going to need to add the base value, or to add to the base value, negative 0.18, so we're really subtracting it. And we're also going to be using the meta value as well. So there's going to be 7.36 minus 0.18 minus 0.11. So I'll repeat that, and hopefully you have your NMR table with you. Those were passed out in class, and they're available online. We start with our aromatic base value of 7.36. We add to it negative 0.18. You can just subtract it, it's fine, but whatever. Add negative 0.11. And assuming I did all my math right, and I trust my calculator, this comes out to 7.07. So we're predicting what the spectrum would look like. We would have two singlets for para-xylene. One of them is centered at 2.5 and the other is centered at 7. And those are two relatively simple examples for predicting the number of signals, integration, splitting, and chemical shifts given the actual structure of a compound. So I think now would be good if you wanted to go ahead and go to the worksheet that's online and practice a couple of problems. I think it's like number 1 will be a couple of examples. I think there's 5 examples where you can practice that with other molecules. So have fun with that. Otherwise, we can continue to the other side. So I do want to like stop here before you actually go through and do structural elucidation, which is when you're given, you're not given the structure, you're just given all the stuff that we just put in the table. It's tricky, and if you don't know how to do it in the forward direction, like if you don't understand all this stuff that's in the blue and the green and the red, you're going to have a hard time with structural elucidation. So I'm even going to stop here and say, you may just want to watch this part of the video now, work on the homework, get some help in office hours, or we're going to give you some time to work on the worksheet in lab next week. And then once you feel solid on number 1 of the worksheet, the predictions, then you can start working on structural elucidation. So that's just fair warning. But since this is one video, we're going to keep it going. Okay, we're going to do our best to predict the structures given some interesting pieces of information. We're going to use the molecular formula to calculate the degrees of unsaturation. We're going to use these IR stretches to identify what functional groups might be in the molecule. And you might not know the exact functional group, but it can like maybe at least help you with the type of bond. And then this is the really cool puzzle building part. You're going to draw some structure fragments based on signal information. So that's kind of the main process, like the 1, 2, 3, and then you put it all together. All right, so here we have our molecular formula for our first example. We have C3H6O. We're going to compare it to the fully saturated formula, CnH2n plus 2. So if it was fully saturated, it would be C3H8. You can see now there's a difference of 2 protons, which means we have 1 degree of unsaturation. That's all we know. From here, we have a stretch in the 1700 region, which tells me that we have a carbonyl. We don't know whether it's an aldehyde, a ketone, an ester. Actually, we know it's not an ester because there's only one oxygen, but it could be a couple different types of carbonyls. And this peak at 2900 tells us that we have a CH bond, and that this CH bond is in the sp3 range. Now, if you have a hard time coming up with this on your own, be a good time to review just a couple different ranges that you have in the IR tables that are online. But I'm not going to switch to those. Now, the cool part. We have an NMR fragment of a 2.0 ppm 3H singlet. I like to start with the 3H part first. So let's start with that. So that just tells us we have a CH3 group. And the fact that it's a singlet tells us that it's connected to a carbon that has no hydrogens attached to it. Okay. Now we want to consider that we have a higher chemical shift than normal. And by that I mean, let me switch screens. If those hydrogens that are the CH3 group, if it was just a regular old alkane situation and nothing interesting nearby, it would be a little bit lower. So I realize that 2 is very close to 1.9, but we know that we have a carbonyl happening. So this actually points us a little bit better to the fact that we have a hydrogen next to a carbon that's next to a carbonyl. So this range isn't going to be as interesting to us. What we really care about is this range of 1.9 to 3.3. That's a bit more accommodating to what we have in store for us. And I started with this example, very low molecular weight. There's only 3 hydrogens. And so actually these 3 hydrogens, I just realized, don't actually account for all the signals. This is supposed to be a 6 hydrogen singlet. And from that, you couldn't possibly have 6 hydrogens connected to 1 carbon. So really what we wanted to do, we should have 2 of these signals. There's only 3 carbons total. So really there's 2 of the green part, and there's just 1 carbon in the middle. And in order for the chemical shift range to really make sense, that carbon must be the carbonyl. So there's 2 of those. There's really only one way to put this structure together, and that's where we have 2 CH3 groups on either side of a ketone. This is also known as acetone. Okay, so this is what the NMR spectrum and IR spectrum of acetone be expected to look like. Only 1 signal because there's only 1 type of proton in that molecule. So I might recommend that you pause the video at this point, maybe review it on your own. Otherwise, we're going to move on to the next example. Here we have a couple more atoms involved, like more carbons. So there's more possibilities for what we could draw. We're first going to figure out the degrees of unsaturation. A fully saturated hydrocarbon would have a formula of C5H12. And when you're determining degrees of unsaturation, hopefully you remember that you do ignore those oxygens. So this compound actually has 0 degrees of unsaturation. We have a lot more going on in this molecule. As you can see, we have many more proton NMR signals, the same number of IR signals. We have an interesting stretch in the 3300 range, which tells us that oxygen is very likely, that definitely involved in an alcohol or an OH bond. And once again, we're going to be expecting some CHs in there, and all the carbons are going to be sp3 hybridized. Now, there's probably going to be more than just this one. I mean, I was just trying to keep this simple that, you know, the 2900 region tells us that you have alkane stuff. We're going to look at each individual peak and determine some good stuff about each one. So first of all, we have a 4 ppm 1H broad singlet. And the fact that it's a broad singlet tells us that it must be that OH. Now that might be new information to you. We never have splitting through heteroatoms, so we have no idea what's going on with that carbon and how many hydrogens are attached. We just know that that's the 4 hydrogen, or sorry, the 4 ppm signal. OHs can show up anywhere between 0.5 and 5. They kind of show up wherever, depending on what else is going on in the molecule. So that's one that, this is one fragment that we have, just another confirmation that we have an alcohol. Next, we're going to be looking at this 3.5 2H triplet. And we start with the simple part. The integration tells us to CH2 group. And I'm going to highlight so we know that we're talking about CH2. It is next to a certain number of protons that would make it a triplet. So if you remember the N+1 rule, N+1 rule, and this is equal to 3 in this case, then that must mean the number of neighbors is 2. So it's next to another CH2 group. Now, last thing that we want to draw attention to is this chemical shift. This one is pretty de-shielded, and we already know there's an alcohol in our structure, so we're pretty sure that that carbon, that set of hydrogens, is going to be next to that oxygen. And we know that that is an OH group from another piece, so we're starting to like build our molecule little by little. Cool, so that's a pretty solid fragment. Next fragment, we're going to deal with this 1.61H non-net, and I haven't, in the table I don't actually have a non-net, but this is a 9 peak signal. Okay, so if the N+1 rule equals 9, then we know we have 8 neighboring protons, and clearly we can't have 8 neighboring protons on one carbon, so it's going to be split into a couple different things. But let's start with our actual fragment. It's a CH because it integrates to 1 hydrogen. The range is 1.6, meaning it's probably close to that alcohol, but not quite close enough for it to, you know, be high like 3.5. So it looks like there's only one set of hydrogens that's right next to that alcohol. But it has 3 different other things that it's going to be attached to, and those 3 other things can't be hydrogens because it's just a 1 hydrogen signal. So those are carbons, and again, they're not oxygens because we already ruled that out. So we're going to have to split up these hydrogens. So we're going to have to figure out how to make it into 8 signals, or basically like the maximum number that we could have around here. So I would actually put 2 of them, I would max them out and say, okay, well, there's going to be 6 of them that account for those methyl groups. And then on the other side, there's only 2 left, so it must be next to a CH2 group. So we actually are seeing that this is a little isopropyl fragment. And then we just don't know what's attached here, just like over here, we didn't know what was attached to that carbon. So we're starting to, once again, continue to build fragments, and we might even already have some overlap. Next, we'll go to this 2H quartet. So we have a CH2 group. If our N+1 rule equals a quartet, which is 4, that must mean that we have 3 neighbors. So we're focusing on this CH2 group because that's the central signal of 1.5, and it's next to a CH3 group. Okay, so we have a CH2, CH3 group. Or do we? I want to remind you that this is going to be one possible way of doing it, but it doesn't have to be a CH3 group right next to it. So that could be one fragment. But if you take a look at what's going on over here, it's not really very consistent because you know that these CH3 groups are not next to CH2 groups. So we want to think a little bit more broadly. An option actually could be, well, what if it was a CH2 group? And we're going to highlight, this is the actual peak of interest. What if it was next to a CH2 group on one side or a CH group on the other? Ooh, right? So that's like another possibility. It couldn't possibly be a CH2 group with 3 CHs around it, because then you would be violating carbon's octet. So we have 2 different options. I wonder which it is. We'll figure it out, but those are, you know, just options based on 2H quartet. It's the chemical shift is 1.5, so again, we're not right next to the oxygen, but we might be nearby. Finally, we're going to look at our 6H doublet, and this 6 hydrogens must be 2 equivalent methyl groups. They are connected to the same carbon, which is attached to 1 hydrogen, and that carbon is attached to just some other carbons. So now we have an even bigger fragment. We can see an overlap with the green. So we're focusing here on these CH3 groups that are coupled to the hydrogen on the carbon next door. And then, you know, what's going on this carbon? That's like the remaining piece, the remaining fragment. Okay, so now we have all the different pieces. We should be able to put it all together. We're going to label these guys as, actually, no, we're not going to label them. We know on one end we have an isopropyl group, right? So these are going to be, there's a hydrogen right there. That's going to be connected to a CH2 group, another CH2 group, and an OH. So now I'm going to kind of recap and make sure we accounted for everyone, because this is how our pieces actually overlapped. First, we had this 4 ppm 1H broad singlet. So that makes sense because there's no splitting through heteroatoms. We then had next, closest to the oxygen, we had a 3.5 ppm 2H triplet because it's next to 2 hydrogens. We had a, let's see, 1.6 part per million, 1 hydrogen, oh, sorry, I'm doing this out of order. The 1.61, the single hydrogen one, is the one that's part of the isopropyl group. This is a 1 hydrogen nonette. It had 9 neighbors. So here's the one here. It has 6 from the methyls, and then the 2 from the methylene. Okay, and I just paused the video so I could add in, I think something that'll be really useful is actually drawing in all of the different hydrogens so we don't lose track. Next, second one on the blue team, we have our other CH2 or methylene group, and these 2 hydrogens were a quartet. So now we can actually see the coupling between these protons and those on the right. So we have 2 protons on the left and 1 on the right, which adds up to 3. So we have 3 neighbors, and 3 plus 1 is 4. This is how we end up with a quartet. The chemical shift was at 1.5. We're a little bit closer to that oxygen, but not so high that it really increases the chemical shift by that much. And our final one, just to confirm that we have everyone together, these are our CH3 groups. This is our 6 hydrogen doublet. Those 2 are equivalent, and the chemical shift is pretty low. It's centered at about 0.9. Now, if you wanted to go through and actually double check all of your answers, I 100% welcome you to go ahead and do that. This is using the same method that we had above. You would go through and find the general chemical shift range for each, but even better, you would go over to the alkyl shift range. So this is the additive table once again for the alkyl shift range. When you had those methyl groups, you would start with 0.9, which I already highlighted, and you're going to be adding in, if we have only if we're close enough to that oxygen, which we're actually not. So we actually have to be minimum 3 carbons away for it to make a difference. So if we're right next door, we can see that adding an OH group, oh perfect, would be adding 2.3. If we're 2 carbons away, we add 0.3. If we're 3 carbons away, we add 0.1. Sorry, cut off a little bit. So in our molecule, I'll just draw it here so we can see that again. These hydrogens are too far away. The hydrogens that are over here are in the alpha position. These are in the beta position. Those are in the gamma position. So you are going to use those additive parameters for those 3 sets of protons. But the chemical shift for the hydrogens in the methyl group are too far away. The only additive parameter you could add would be this, and it's all just adding 0. So just having alkyl groups doesn't really affect the chemical shift. Those are not particularly electron donating or electron withdrawing enough for it to be observed in NMR. So that's how you go ahead and double check your answers, either using the methyl point to start. You might be using the methylene group for your CH2 values, and you might be using, or you will be using, your 1.5 for the methine values. So after you propose a structure, always a good idea to go back through and double check that your work makes sense. that is how we do it. I hope that is helpful for you in working through the NMR worksheet. There's 5 problems where you predict stuff. There's 5 problems where you propose a structure. And then there's 2 additional problems where you propose a structure where I actually give you the individual spectra so you can see some more of what NMR spectra look like. Thank you very much for watching. I don't have a timer on here, so hopefully this didn't go for too long. But yeah, have a good one. Bye.